All right. Good morning, everyone. So thank you very much for the introduction. Today, I'm going to talk about some of our recent research on environmentally equitable AI. So let me start. So as we all know that we have been using a lot of AI models like ChatGPT, Gemini, and these models are getting bigger and bigger. And some of them have like hundreds of billions of parameters. And these larger and larger models are definitely requiring more and more computing. And there are many of them are just be trained and deployed in AI data centers. And although there's a lot of uncertainty about the future demand of AI computing, but one thing we're pretty sure about is that this AI computing will be requiring a lot of energy. So this IEA projects that by 2026, the global AI computing will consume at least 10 times the amount of energy that we consume now. And this is roughly equivalent to a small country like Belgium or the Netherlands. So clearly, although we are making a lot of progress in terms of decarbonizing the grid, but the power grid is still primarily relying on the coal power plants. So there's a huge carbon emission associated with this AI computing. And of course, carbon emission has a global impact. But beyond the carbon, what are the environmental costs? We also see this water consumption because when we generate the electricity, there's a huge amount of water consumption. And if you look at this white steam, they look like a carbon. They're not really carbon, they're water because carbon is really invisible. And also when we when we generate the electricity using coal power plants, there's a huge amount of air pollution problem and thermal pollution problem. So more critically, these environmental costs are actually local beyond the global carbon impact. So let's take a look at these impacted communities for generating the electricity to power AI data centers. So this is a map showing the Colorado River basins serving 7 states in the western part of the US. And we can see that there are a lot of coal power plants that are generating electricity to power data centers in Arizona, and some of them in California as well. So if you look at these communities, they're, compared to other communities, they're disproportionately impacted by the environmental cost of AI. And let's listen to the local voice. What do the people say about this AI computing when they know that their communities are generating the power, the water for supporting the AI computing? So people definitely are not happy with that because they know the AI, the data center will dry up their water resources and polluting their air problems. So. And also, in some cases, like let's say in Virginia, which is a data center capital, the power plants are actually located in West Virginia, and there's a huge issue with the utility rates increase due to the power plants and also transmission line construction. So additionally, these different parts of the world are not equal. If you look at the carbon intensity, which is sort of a proxy for the amount of air pollution that we generate for electricity. So this is not equal. This is showing the carbon intensity map of different states in the US. We see California is relatively greener compared to many other states, but states like Missouri, Utah, they're not really as clean as California. And if you look at this water consumption, there's even more disparity across the world. So we did some of the estimates for AI computing's water consumption. So the number we showed that was that if you had a conversation with ChatGPT I mean, of course, this was based on the GPT-3 because GPT-4, which is being used by ChatGPT now, is not an open system. So given this estimate, we can, if you have like conversation with ChatGPT for 10 to 50 queries, there's a 500 milliliters water consumption, depending on where you are. And so this is what we call environmental inequity. So if this issue has been recognized by several international organizations and governments. So if you look at this AI Now Institute, they compare this AI's uneven distributions of AI's environmental cost to this racial capitalism. And the state of California also recognized the need of fairly distributing AI's environmental costs across different regions. So how are we going to be able to address this equity when we try to minimize AI's environmental cost? So one of the solutions that we are studying in our research is so-called equitable geographical load balancing. So essentially, we're trying to balance the workloads of AI computing among different regions, because when you move the workloads computing, you're also moving the energy demand and also the environmental cost. So the idea is very simple. So we have these user requests from different parts of the world, and these data centers are located in different parts as well. And we're just moving these workloads in a dynamic manner depending on the real-time real-time condition of the system. So one of the criteria that we consider is a fair distribution. And how do we encourage fairness? So, before we talk about how, let me give you an example of what I mean by equitably distributing AI's environmental costs. So let's look at the toy example. Here we have two different states, California and Arizona. Both of them are highly water stressed, but comparably, California has a better situation than Arizona. So suppose the water efficiency for processing one request in California is 1, in Arizona is 2, and we have three user requests. What are we going to do to minimize the total water footprint? Is, of course, very simple. We just move all the workloads to California, and then we end up with the 3 units of water consumption in California, but 0 water in Arizona. This seems to be minimizing the total water footprint, but it's not really equitable. Another way is, let's split the user requests between these two different states using a ratio of 2 to 1. In the end, California will only consume 2 units of water, and on the other hand, Arizona also consumes 2 liters of water, 2 units of water. So this is what we call equity. Of course, you have to do some factoring of the local conditions, but this is sort of illustrating our key idea. So mathematically, to encourage equitable distribution of the AI's environmental cost, we're adding a equity regularizer into the objective function. And this here, in our research, we're using the LP norm. So essentially, this is trying to balance the long-term environmental cost. XT is your workload distribution, and CT is the environmental cost matrix, like the water and the carbon intensity. And then multiply these two things together, you'll be able to get to your long-term average environmental footprint across different regions. So this LP norm is very flexible. If you choose a p equal to 1, that reduces to the existing simple cost of a simple case of minimizing the average environmental footprint. So let's look at a simple case of minimizing the water. So we choose p equal to 1, and in the end, you might end up with of course, you minimize the total water footprint, but the highest and the average is pretty different. So, but if you increase the p value, when p goes to say 10 or 100 or very large value, you're promoting more equity. And so this is on the right-hand side, we can see that if you, with a bigger value of p, then the worst to the average ratio will be much, much smaller. So this essentially, we're making sure the AI's environmental cost is more equitably distributed across different regions. So this is the key idea and the novelty of adding this equity regularizer. So then the problem formulation is pretty simple. The first term is your traditional cost. You're minimizing the energy cost or the some of the performance latency cost. And so I'm not showing the details of the cost formula, but it's basically whatever you did in the past. And the second term, this is something that we added here, which is this equity regularizer. And so this is promoting the fairness for distributing AI's environmental cost. But this term, the equity regularizer, although it's very intuitive, but it's really hard to optimize because it's not separable over time. And if you work on optimization, you know that this is really challenging when we try to do this online optimization, since you don't really know the future, but this equity regularizer depends on all the future information. So what we do to solve this problem in an online manner without knowing all the future is to reformulate the problem. And we can mathematically show that this problem has the same global optimal offline solution to the previous solution. And we just add another variable, z, which is the auxiliary variable, indicating the budget for environmental costs. So this is like how much you want to put, what is the target environmental cost across different regions. And of course, this ZT is a variable that we have to determine online. So essentially, we're trying to, we have a new problem, which we try to minimize the total cost plus some equity regularizer subject to a constraint, a long-term constraint. And this is still a hard problem. But still, compared to the previous problem, this is a lot easier now, since we can convert this long-term constraint into the Lagrangian relaxation form. And here we have the Lagrangian, and which essentially we're trying to update this dual variable, which is the Lagrangian multiplier. And if you know this Lagrangian multiplier, the problem is super easy because you just minimize at each time, you just minimize the xt, which is your geographical load balancing decision, and zt is your dynamic environmental cost budget for each location. And so the algorithm is simple. At each time t, we get the cost function, we get the carbon water intensity, and then we try to select our GLB decisions, and then update our dynamic budget, ZT, which is the auxiliary variable. And what about the dual variable mu-t? That's also pretty simple. We just updated using mirror descent algorithm. I'm not showing the detail, but if you're interested, you can look at our papers. So, and also this algorithm it has some theoretical support. So I'm showing the first informal theorem. So as t goes to infinity, we can show that our average cost compared to the optimal average cost, there's a gap, of course, but the gap is bounded by a constant term, and this term depends on the range of your environmental cost factors. And so how do we reduce the O1 term? And to our knowledge, there's no way to reduce this O1 term completely. But the key reason is that we're comparing our algorithm with a very strong baseline. But if you sort of consider a slightly weaker baseline, which we call R delta constraint optimal offline algorithm, and this algorithm is solving the same problem as before, but it just has additional constraint in the sense that its total average R is a frame size. The frame level environmental cost is not too much different compared to the global average. If you add this delta constraint, then we can show that our algorithm compared to this is still strong, but slightly weaker baseline. The difference becomes a sublinear term, and plus additional total variation term, so which is indicated by your constraint delta. So if your delta goes to infinity or linearly increasing with respect to t, then this result reduces to the previous theorem. But if delta is sort of smaller or sublinear in t, then essentially we're able to show that the asymptotic regret between our algorithm and our delta constraint offline algorithm is essentially 0 when t goes to infinity. So, all right, so this is just some of the theoretical analysis. If you're interested, we can talk more about it offline. And now I'm going to show you a very simple case study. So we're considering a situation where there are 10 different data centers, and 4 in the US, 4 in Europe, and 2 in Asia. And so here are the details of the here are some of the details of our simulation settings. And we consider the Bloom, which is a large language model inference trace. Of course, we scale it up to our application. And we considered 2 environmental costs, water footprint and carbon footprint, because carbon is a proxy for the amount of air pollution you generate for each location. So here is one of the snapshot of our results. So while EGLB, this is the actual values, but compared to the existing GLB baselines, let's say the GLB that minimizes the energy cost, we're able to reduce the peak to average ratio, or the worst case to the average case environmental cost. The ratio is reduced significantly from, let's say, 1.6 something to 1.3. And compared to our EGLB and the EGLB offline algorithm, we're fairly close to the offline case. And if you compare to the carbon case, we're able to reduce the existing GLB carbon, just minimize the energy cost plus the weighted carbon emission, but it doesn't have although it reduces the total carbon, but it has some very high peak to average ratio. But our case is so we're able to promote equity by reducing this ratio, because this means the amount of air pollution that we generate in each location due to the AI computing is sort of more uniformly distributed. It's not like hurting some regions disproportionately. So the overall conclusion is that EGLB can mitigate AI's environmental equity at a smaller cost. Of course, nothing is free, but I think our cost is reasonable. So let me then conclude my presentation. So we need sustainability, but we also need equity, and this is the environmentally responsible AI we need. And that's it.